So bonding in metals. Bonding in metals is a bit different than bonding in like molecular compounds or in ionic compounds. So we've looked at trends in ionization energies. The metals are going to have low ionization energies. They will fairly easily lose an electron, and that makes a positive ion. But when you just have metal atoms, there's no one to give that electron to. So what happens is, in a metallic solid, each metal atom donates one or more electrons to this pool of electrons. We call it an electron sea. So it's like this ocean of electrons. And so we can think of sodium metal, the element, as being an array of sodium ions that are surrounded by this sea of negative electrons. So even though positive sodium ions would repel each other because they're swimming in this sea of electrons that have negative charges, they're actually attracted to each other. So this helps us to explain some of the properties of metals. Metals are conductive. They conduct electricity. In this model, these electrons are not attached to a particular atom, and so they're free to move. And so the electrons can move freely throughout this metal, and the metal will conduct electricity. It also explains the properties of malleability and ductility. So if you take a piece of metal and you bang on it with a hammer, you're going to dent it, but it won't shatter. And if you keep pounding on it, you can flatten it. These attractions that are holding the sodium atoms or sodium ions together are non-directional. They're being attracted by the electrons in all directions, and so if you apply a force to them, they'll just move out of the way a little bit. They're not going to shatter like an ionic compound, where if you put stress on that and break that bond, the whole thing is just going to shatter along a plane. Okay, so any questions about that? It's kind of strange, huh? And then just a little bit about the Lewis structure for ozone. So oxygen, O2, has a double bond. Ozone is O3, and this is kind of strange. Ozone has an odd electron configuration, a Lewis structure. So let's see. We've got 18 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's about the best Lewis structure we can do for ozone. And we see that we've got one with a 0 formal charge. This one has a positive formal charge, and this one has a negative formal charge. But there's actually resonance here because we have this double bond and a single bond. And so it's not that really we have one double bond and one single bond. We actually have two that are like 1.5 bonds. So they're intermediate in strength between single and double bonds. So we have ozone in the atmosphere, and as UV light comes from the sun, this UV light, which is harmful, did something happen? Oh, train? Yeah. Well, it's something. Hopefully nobody will get sick. If you start feeling nauseous because of the shaking screen, just look away. We've tried to fix that and it's not possible. Where was I? Okay, ozone in the atmosphere, right? So ozone will block the UV radiation. The UV light has enough energy to break the bonds in ozone, which are weaker than the bonds in oxygen. It does not have enough energy to break the bonds in an oxygen molecule. So the ozone can absorb the UV energy because it will break a bond. It will then form oxygen and an oxygen atom, and then those will recombine to form ozone. And so the ozone layer protects us from excessive UV radiation by absorbing it. And it can do this because it has this resonance structure with the 1.5 strength bonds. Any questions?
So what happens after